Chapter 5 is on time series analysis and forecasting. Many of you who are eco or finance majors will see a lot of this in your upper level courses. Time series simply means that we're going to collect data based on time, weeks, months, and especially quarters in business. We're going to analyze our historical data and then use it to project or forecast into the future based on those long-term trends we see. It usually assumes there's some pattern that's going to continue on into the future. However, right now during COVID, we're going to have completely separate models because nothing is normal. So once again, the idea of forecasting is that we want to reduce our risk in making better decisions with these models that we can get using time as a variable. These are the assumptions that we use in forecasting. All of our techniques assume the same underlying fundamental system that existed in the past will continue to exist in the future. Again, during COVID, this assumption is invalid. The next one is that forecasts for groups of items tend to be more accurate than forecasts for individual items. If we're Target stores, it's better to try to forecast for the overall store sales than to forecast simply for jean sales. The next one is that our accuracy is going to decrease as time progresses into the future. We're going to have a rule of thumb that says forecast only 3 to 5 time periods into the future. More than that is extrapolating to the point that we'll have large errors in our predictions. And finally, know that forecasts are seldom perfect, just like the weather forecast. So just how precise are these models? Depending on what type of methodology we've used to try to forecast, we'll get different error outcomes. MAPE is the mean absolute percentage error, and MAE is just the mean absolute error. Those are in our specialized models that we use in time series and jump. MAE is found simply by taking the absolute value of each residual and finding the overall average of them. Then root MSE is what we typically see reported in our regression output. We want to be careful and only compare root MSE to root MSE and MAE to MAE. So every now and then we might be comparing a specialized model to a regression model, and we'll have to calculate the MAE for that regression model. The lower the error term, the better the model. There are 4 basic components to a time series. The secular trend is going to show the long-run overall direction of how Y is moving over time. So it may tend to go up or down with time. We also have secular trends that are logarithmic, and we'll look at those when we have increasing values at increasing rates. Then we have cyclical variation. That's more of a business cycle. When we're going through times of prosperity, recession, depression, recovery, those are all cyclical and require more complicated models from econometrics to predict those. Then seasonal variation is a wave-like pattern, and it happens over and over every year with the peaks at the same time and the lows at the same time. Finally, we also have irregular variation, or ERA. That can be classified into 2 groups. Episodic irregular variation is unpredictable but identifiable. In other words, if sales just drop one time and we go back and say, oh, that's when we had a tornado or a hurricane or COVID, It would explain why there was a drop, but we might not have predicted it the year before. Then residual irregular variation is everything else that's just left to chance. We can't identify it, and we also can't predict it. There are different techniques for forecasting and predicting with time. The first is called a naive approach. It simply states what happened today will happen tomorrow. So if last year's sales were $1 million, we'll just assume next year's sales will be $1 million. That's our least favorite way of predicting. The next is called a moving average. It simply takes our data, especially if it's in a linear or wave-like fashion, and smooths out the lumps and bumps to show the overall trend. And then exponential smoothing allows us to weight the values and give a heavier weight to newer values than to those in the past. Some of the models we'll look at include trend lines. These will show the secular part of a series. They may be linear or exponential log depending on the scatter plots that we see. Then seasonal trends can be predicted using seasonal exponential smoothing models or with multiple regression models that use indicator or dummy variables. Finally, the cyclical trends require econometric models that are beyond the scope of this course. This is called a moving average. Notice you have cable sales. And so I've got the values 52, 67 through 73. If I ask for a 4-point moving average, look at the column entitled 4MA. It takes the first 4 data values, average them up, and puts them over under the 4MA column. So we get 64.5. Then it drops the first data point, 52, and adds up the next 4 data points and averages those. It puts 65.8 next. Then we drop the 67 and average up the next 4 values. So that's why it's called a 4-point moving average. In this data, you notice that the original values for cable sales had all these ups and downs. But when we calculate the 4-point moving average, it smooths out and we can see a slight upward trend in sales. So when do I use a moving average? Again, it's useful just to see the overall trend or smooth it out. It's also good if I have somewhat of a linear up or down trend to show what's going on there. We can calculate seasonal indexes from the moving averages. And we can also find an estimate for irregular patterns that don't have any true up or down shape, but just to smooth it out and see what's going on. There are 2 types of markets. I'm sure you've heard these terms before. We have bull markets, and the definition of those are when the 50-day moving average is above the 200-day moving average. The point where those cross is called a golden cross. So that's a single point. But the overall time period is a bull market once we go above the 200-day average. The opposite is a bear market when the 50-day average is below the 200-day average. And the crossing point is called a death cross. And that signals we should sell the stock. There are 2 types of moving averages. The simple moving average assigns the same weight to each observation in the set. But a weighted moving average typically assigns more weight to the most recent value and less weight to past values. the sum of the weights we use must equal 1. So for instance, if I assign last year's data a 0.3 and this year's data a 0.7 weight, that would give a sum of 1. Let's compare a plain moving average and a weighted moving average in an example. Six Flags operates Hurricane Harbor, and you're interested in trying to predict attendance based on the year. So our most past year is in 2007. It will receive a weight of 0.2. The next year in the middle is 2008, 0.3 weight. And then the more recent year from that series is 2009, which will get a 0.5 weight. So together, 0.2 plus 0.3 plus 0.5 sums to 1. When I work out the weighted moving average for that, we get a value on the next slide. So that would be 9,511.5 as a weighted moving average. If I compare that to a 3-point moving average that's not weighted, I get 9,341.67. So in the next slide, we'll graph out each method and see if one seems to be more smooth than the other. In this case, the real data is seen in the dark blue line on top. Then we have our weighted moving average in the aqua blue line. And it's very close to the same as the plain 3-point moving average in green. So in this case, it probably wouldn't matter which method you chose. Let's take a secular trend for IBM sales and try to forecast for it using annual values as time, or your X variable. So we get a linear fit of IBM sales equal 123.26 plus 0.79 times time. So we can plug in values out there beyond time periods, say 28, into time periods 29, 30, 31, 32, and forecast for IBM. We don't want to go too far again. Our R-squared value is 92.05, so about 92% of the variation in IBM sales is explained by time. That would mean 8% is unexplained. Then if I looked at the root mean squared error, we could say that approximately 95% of IBM sales predicted will be within plus and minus 2 times 1.95, or about plus and minus 2 times 2, or 4. I notice that I have 28 observations. If I said, see if time is a good predictor, you could look at the probability of t, see that it's less than 0.0001, and know that definitely time is a good predictor. Here's some cyclical trends. Now, they wouldn't actually be over one single point. It might be over 3 or 4 years before an economist would say we're definitely in a time of prosperity or depression. But I always think of it as peak prosperity, and then the deepest trough would be depression. Expansion or recovery is the going up time period, and then a recession is the going down time period. We, again, will not try to model this. You would need to take an entire class in economics called econometrics for those kind of models. In this slide, we see a seasonal trend. We have a regular wave-like pattern reoccurring every year. So at the same quarter within each year, things are up. In this case, it appears to be quarter 4. See the peaks at 4, 8, 12, 16, 20? That means those are the uptime quarters. So I probably have something like snow skis that are selling quite well in that 4th quarter. So we determine that we want to use one of two methods with seasonal trends. Here we have a multiple regression model with 4 variables in it. T for time, then Q1 for quarter 1, Q2, and Q3, but you notice there's not a quarter 4. We'll get to that later on in discussion, but we always leave out one dummy variable in order to make the model more parsimonious. Nonlinear trends, as you see here, might be exponential in nature, where we have data that are increasing by increasing amounts or decreasing by decreasing amounts, rather than in a linear trend-like fashion. When data seems to be moving like this, we're going to have to account for this curvilinear pattern. In this case, we'll use the exponential log. So here's a model with sales increasing at an increasing rate. We go into jump and we run a regression, but before we do, we transform y into an exponential log. So we get the fit log of log sales equals 3.59 plus 0.332 times t, or time. We have an R-squared value of 0.9864. So over 98% of the variation in the log of sales is explained by time. We have a root mean squared error of 0.226, and we definitely have a good predictor. When you look at your t statistic for time, it's 35.12 with a p-value less than 0.0001. So you see your actual prediction expression or the equation. And remember, when you see EXP, that's saying this is a log value. So we would write log sales equals and then put the rest of the expression in there. I don't have to work it out. I can use Prediction Profiler, and I plugged in 20 for the next year for the data. When I do that, the predicted sales are 28,220.85. My 95% confidence interval is within the brackets for the mean sales. There are a few more other models we'll be discussing later on in another presentation. For now, study this part.